everyone. In this video, I will be solving GATE 2019 chemistry question. It's question number 3. It carries mark 1. So this question states that among the following carbon allotropes, the one with the discrete molecular structure is. So we are given 4 different options. First, diamond, alpha graphite, beta graphite, and fullerene. I am guessing that you might have already have an idea, but let's just jump into some basic and just discuss the structure. So, uh, this one, this two, and this three different structure correspond to which given option. You can give me some answer, or I mean, just you already know. So first is obviously diamond structure, second is for graphite, and third one is for fullerene. So the second one is also we are given with two different graphite, alpha and beta. We will discuss it in further slide. The first one for the diamond. So diamond is a diamond's carbon atoms are actually reported to form strong chemical interaction with the 4 other carbon atoms. So there are one carbon atom is making bond with other 4. So forming a flawless tetrahedron structure that extend throughout the crystal. So I have highlighted this one in red color so that you can understand that this structure is not actually discrete. The carbon atom are sp3 hybridized and the carbon-carbon atom bond lengths are equivalent. The second structure is unit cell of alpha graphite. So this structure is actually a unit cell of alpha graphite. We will look into it. So the graphite actually consists of sheets of triangular planar carbon. So I have I have also highlighted this one in red color so that you can just have a look and understand that this is also not a discrete one. So the individual layers are called graphene. In each layer, the carbon atoms are arranged in a honeycomb lattice with a bond length of 0.142 nanometer. And the distance between planes is 0.335 nanometer. So the bonding between layer is relatively weak. It is a van der Waals bond and are often occupied by gases. This is some extra information. Okay. So the two forms of graphite are called alpha, which is hexagonal, and beta, which is rhombohedral. So their properties are very similar. They differ in terms of the stacking of the graphene layer. So what does it mean? It means that in alpha graphite, the stacking is ABA pattern. So here you can see this. If this is A pattern, it is repeating in the third one. This is A pattern. It is repeating in the third one. It is repeating in the third one. often occupied by gas. Now, what does it mean? It means that in alpha graphite, the stacking is ABA pattern. So here you can see this. If this is A pattern, it is repeating in the third one. So in middle, it is a different pattern. So it's called ABA stacking in alpha graphite, and in beta graphite, so it's a ABC stacking, and it is energetically less stable, and therefore it is less common. Coming to our last option, which is fullerene. So fullerene is an allotrope of carbon again. So whose molecule consists of carbon atoms connected by single and double bonds so as to form a closed or partially closed mesh. Now here the highlighted portion, you can understand by this only that this is the one which is discrete structure. So with few string of 5 to 7 atoms, the molecule may be a hollow sphere, ellipsoid tube, etc. in shape and size. So yeah, for fullerene also, it is also denoted, for example, like Cn, where N is actually the number of carbon atoms. So for example, this is C60, and there is C20 also. Okay, so this just denote the number of carbon atoms, including the closed or partially closed mesh. Now, what will be the correct option here? Sorry. So this is one with the discrete molecular structure is fullerene. Thank you.
Yeah, so everyone, if you have listened to the video, have any questions, then you can put your doubts on the chat box or unmute yourself and then ask.
Excuse me, ma'am.
Yeah, yes, Ravindra.
Ma'am, beta graphite is energetically less stable. Could you tell the reason behind it?
So actually when you study in solid state also, so the more symmetric the structure is. So in hexagonal packing also, the A packing was more common. So ABC packing is actually not so common, and it is energetically less stable because of the after some point of the time when the layering is happening, if the pattern is not symmetrically packed or closely packed, then of course it will be less stable.
Thank you, ma'am.
Okay, so I'll move to the next question. So just hold on, because I am saving the longer version of one video in the last. It is for the coordination compound, where microstate concept I have cleared. So just wait for that one. This another one is also the quick question, which is carrying 1 mark. So okay, I'm going to share.
Hello everyone. Today in this video, we will be solving GATE 2019 chemistry question. This is question number 19. It carries 1 mark. This question states that the total number of alpha and beta particle emitted in the following radioactive decay. So this is the radioactive decay, and we have to find out the number of alpha and beta particle. Okay. So before solving this question, let's just move into some basics. Radioactivity is actually caused when an atom, for whatever reason, wants to give away some of its energy. The nuclei of these elements are unstable, and it therefore decomposes or decays spontaneously with the emission of alpha or beta particles. This leads to the formation of some new element with different physical or chemical properties. Now, what are the types of decay? So there are alpha, beta, and gamma rays. So in this form, we observe radioactive decay. So first, alpha particle. It is nothing but helium nucleus carrying charge 2, mass number is 4, and its penetrating power is minimal. Beta particle is electron. It is symbolized as this here. It carries a charge of -1, mass 0, and it has slightly higher penetrating power than alpha particle. So it can penetrate short like skin and some other tissues. Gamma rays are simply electromagnetic radiation with 0 charge and 0 mass. It has a very high penetrating power. Okay. Now, so our question is to calculate number of alpha and beta particle beta particle emitted during radioactive decay. Correct? So for that, let's just assume and make some expression for it. So this X element is getting decay to Y with the change of its mass. Number is A from A to A1 and from Z to Z1. Correct? So and then to solve this, let's just say let X is nothing but alpha particle. We assume it like that, and Y is a beta particle emitted in this whole process. Okay, so this simply makes our equation as so this is X times alpha particle, which is helium, and Y times beta particle, which is denoted as electron. Correct? So to solve the final expression, we just need to make two equations out of this. So the two equations will be number 1. So we have to balance atomic number, which is Z. Correct? So we have to balance atomic number Z here. So simply following left hand side is equal to right hand side. So it becomes Z. So see, Z from here. So this will be equal to Z1 plus it will be X into 2 and Y into -1. Okay. So this will give me Z is equal to Z1 plus twice of X plus -1 multiplied by Y. So this is my equation 1. Okay. Now for my equation number 2, we need to balance atomic mass A, and that will be A is equal to A1 plus 4x plus a mass of electron was 0, so 0y. So this will be equation number 2, and therefore from here directly we can get x value. So this is x is equal to A minus A1 by 4, and this is nothing but number of what? Alpha particle. Correct? And if I substitute x in equation 1, what I will get is, I will get z is equal to z1 plus twice of a minus a1 by 4, and there was minus 1 into y, so it is minus y. So hence I want to find y, so y will be z minus z1 plus a minus a1 by 2. So this is nothing but the number of beta particle. Now to solve our problem, which is 238 of uranium 92 giving me 210 of 82. So to solve this, first I will find out alpha particle. So alpha particle, to find out alpha particle is very simple. Just you need to subtract this and this so that you can get the difference in the mass, atomic mass. So this will be 238 minus 210 divided by 4. Okay, so it will be 28 by 4, which will give me 7. So there are 7 alpha particles. Now, so there are 7 alpha particles. I need to find out beta. So for beta particle, I can also go with this formula, or else I can just mentally do the difference between atomic number. So the atomic number difference is actually 92 minus 82. This is actually giving me the difference of 10. Correct? But if I look here, so I have a total of 7 alpha particles. So 7 alpha particles, that means it will give me 7 into He24. So this should make a atomic number difference 2 into 7, that is 14. So there should be a difference of 14, but actually we are getting a difference of 10. So the number of beta particle becomes 14 minus 10 is equal to 4. And why this is so? Because beta particle is what? It is electron. So the atomic number, it is actually, there is a charge of -1. So this just add up, and therefore it makes, which was actually supposed to be 14 from the alpha particle, but it adds up -1, and then therefore we get a total of 10 as a difference. Correct? So you can also do it in this way. Just find out what should be the actual difference when we know the number of alpha particle, and after that you can actually subtract it from the difference we actually observe. Okay, so this is the number of beta particle. Or simply you can do it from here also by following the formula. So basically your alpha particle is 7, your beta particles are 4 in number. So we have asked a total number of alpha and beta particles. So you need to be vigilant here and then just add these two and you will get a total of alpha plus beta, and therefore we will make it 11. I will recommend you to look into this lecture from Professor H.C. Verma, Department of Physics, IIT Kanpur. And also you can follow the book Principle of Physical Chemistry by Puri Sharma and Patania. So I followed the edition 2001. Thank you.
So any doubt? So yeah, it's a pretty simple one. So let's move into the another question set.
Chemistry question. Question number 18. They state that the maximum number of microstate for D2 electronic configuration is. Before solving directly the number of microstate for D2 electronic configuration, I would like you to introduce the basic, the concept of microstate, how it emerges, and the reason. So let's have a look on the concept of microstate. So this comes from the optical absorption spectra, also known as the electronic spectra of the coordination compound. I take the example of hexa-aqua nickel 2 plus complex ion. It is an octahedral D8 complex ion. So according to ligand field theory, the metal d orbital in an octahedral field T2G and Eg, and so that in for this complex there are 6 electron in T2G and 2 electron in Eg. So LFT predict that the number of electronic transition will be 1, but we find that the absorption spectra is way more complex than the expected. So instead of a single absorption band, we get multiple absorption band. So here LFT is unable to explain this. So the key points here are that the LFT from ligand field theory, we expected only one absorption band, that is one electronic transition, but through experiment we get 3 absorption band, and the reason behind this was that the LFT assumes that there is no electron-electron interaction. However, this cannot be possible as the electrons in d orbitals have repulsive interaction, and hence it affects the energy overall. So what happens when the electron-electron interact? So let's again take one simple example of D2 ion in octahedral ligand field. So we can take a lot of example. For example, this I am here. It is shown for excited state for the same D2 ion, but when it was in ground state, these 2 electrons can be in any 2 orbital of T2G, for example XY and XZ, or it can be in XZ or YZ, or in XY and YZ. So there are again number of microstate possible in ground state itself, but let's just discuss to an excited state example. So if I am saying that in ground state my 2 electrons were in XY and XZ, so in excited state, the transition from T2G to EG can happen in 2 different manner. for example, my XY electron goes from T2G to Z2. Okay, and for the same transition, uh, my instead of my XY DXY electron, my D XZ electron jumps from T2G to EG of EZ2. Okay, so there are in total I have only depicted two microstate with different energy for the excited state, for one of the excited state, we can say. So now, according to ligand field theory, it says that both the excited microstate have the same energy. But however, this is not the fact. The fact is that these two microstate corresponding to the excited state have different energy. And this we can actually simply understand by understanding the orbital associated with these microstates and filling up their electronic density. So, for example, if I choose microstate 1, so the electron density will be such that, so this dz square okay, sorry, and for green, for T2G, it is in XZ plane. So XZ is this plane. Okay, so this orbital will be filled. So this is how my electron density looks like for microstate 1. And again for microstate 2, and the T2G XY. So XY plane, this. So this orbital DXY will be filled. I mean the electron density here. So you can just see that these two microstate 1 and 2 have very different electron density and therefore these two different microstate have different energy because the electrons in D Z square and D either XZ or XY, they interact very differently here. So the complex that will observe to depict these transition will absorb different wavelength of light, and this is actually contrast to what ligand field theory predicts. So to find out the total number of absorption bands, we have to predict the total possible microstate for the D2 ion configuration, for example that we have taken. So here a group of microstate, actually I can just write here. So a group of microstates with the same energy is called a term, and the number of electronic transitions can be predicted from the number of terms. Okay, so yes, coming to the what this electron transitions gives us, that the quantum number which determine how the electrons interact. So the energy of the microstate depend on these quantum number, for which are ml and ms of each electron. This is called the Russell-Saunders coupling of electrons. So what are ml and ms? So ml is the magnetic quantum number of a single electron. and it goes from minus L to plus L. And capital ML is the total orbital angular momentum for total number of electrons. So this is, we can actually calculate as the sum of magnetic quantum number of single electron. And the maximum total orbital angular momentum ML, capital ML value is actually correspond to the quantum number capital L. And this capital L is the total orbital angular momentum quantum number. So this is the quantum number associated to ML. And the microstate in terms due to the angular momentum, we can just write it as 2L plus 1. Okay. The quantum number capital L that we have seen alone does not define the term. So in addition, we must also consider the interaction of the spin of the electrons. For that, ms is the spin quantum number of a single electron, and the capital MS is the total spin angular momentum. So it can be calculated as the summation of spin quantum number of each electron. And the maximum ms value is equal to the quantum number associated with it, which is capital S. And this quantum number is the total spin angular momentum quantum number. And the microstate in the term due to spin is simply 2s plus 1. Overall, the microstate from L and capital S, we can write it as the product. So it is product of 2L plus 1 and 2S plus 1. Now, to calculate the microstate for free D2 ion, for D2, this D orbital here, you can see just the depiction. So we can, we just have to first obtain the total angular quantum number and total spin quantum number. Okay, so we need to find out ML and MS and then the corresponding quantum number, that is capital N and capital S. So that is, here is that ML for D2 is simply the summation of MLI, which is ML1 plus ML2. And this ML1 and ML2 can have actually the value from plus 2 to minus 2 and ML2 again plus 2 to minus 2. So for ML, just the summation, so it will also goes from plus 4 to minus 4. So the maximum maximum value of ML is plus 4. So my L is actually 4 here, correct? And the MS is the summation of MS1, MSI, which is MS1 plus MS2. And this can have the value from plus half to minus half, so that my MS become my total spin quantum number is plus 1 because it is the maximum of MS. So my S is plus 1. And my MS goes from plus 1 to minus 1. So the microstate for a free D2 ion, so the possible microstate and the overall number of microstate for a free ion with D2 electronic configuration. So we can express it in a microstate table. So here you can simply just do ML slash MS. So your number of or vice versa. So you can just define your table by yourself. So here to define the columns I am using ML, and to define the rows I am using MS. So for D2 we have ML going from plus 4 to minus 4 and MS from minus 1 to plus 1. And so it is simple, just here the possible number of microstate corresponding to ML minus 4 and MS minus 1. It is actually not possible due to Pauli's exclusion principle. And this is that MS value minus 1, meaning my ms1 plus ms2 should be -1. That is, both of them should be of same spin, -12 and -12. Also, my -4. So this my -4 gives me the ml value -4 here. So this just two electron cannot be in the same orbital with the same spin. This it cannot disobey Pauli's principle. So therefore here there are 0 microstate, and similarly 0 microstate not possible in this column, this space of ml value +4 and ms value -1, and same with the ms plus 1. We have no microstate not possible here too. And the other space, for example, here the ml value, which so here the L value, you can see that ml1 is, for example, 2. So my ml2 is -1 here. So both of them can have the summation of -2 plus -1, giving me -3, and with the spin of -12 each, so that they are following Pauli's principle, and therefore their number of microstate is actually 1. Sorry. Yeah. So again, similarly, if we go on filling these, so you can see that the maximum number of microstate is in where ml is equal to 0 and ms equal to 0. So there are a total of 1, 2, 3, 4, 5 set of microstates, making 5 terms. Okay. So in total there are we get a overall number of microstate in this table. We arrive at the number of 45. So for D2 we get a total of 45 number of microstate. So this goes with the formula number of microstate n factorial n minus r whole factorial r factorial, where n is the total number of electrons orbital can accommodate. So for the case D2, my total number of electron that D orbital can accommodate is 10. So it becomes 10 factorial upon 10 minus number of electron. R is just the given number of electrons. So it's 2 whole factorial and 2 factorial. So this will give me the value 45. For this formula, this is actually the number of microstate. This is based on the term symbol that we are given, because as D2 have a total of 5 terms. So term symbols. So for each term symbol, we can find the number of microstate associated with it using this. And for all those 5, if we sum all these up, then we get a total of 45 again. So for reference, you can check out the book Coordination Chemistry by Ajay Kumar, and for NPTEL reference, you can check the video lecture from NPTEL, Optical Spectra by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. This is the link for it. Thank you.
So any doubt? I know this is the longer version of calculating number of microstate. It was a simple question carrying 1 mark. You can just remember the formula and put it. So I tried a way of approaching it by telling you some concept, in the way that I also get to know this microstate table. So if you guys have any doubt regarding that. So I will share, actually interestingly I was working on this video, and yeah, so that particular concept of I don't know if you guys already knew it or not, but I learned that formula 2l plus 1 multiplied by 2s plus 1. I encountered that formula is actually only for term when you are given some term symbol, like 3s for example is the ground state term for the D2 ion. So I encountered that formula is actually used to solve the number of micro state associated with each terms. So when you solve this, okay, I just go like here. So this formula is actually only used when you are given any term associated with D2. So after you know every terms and you calculate number of micro state associated with each term and then sum them up, you will get the total of 45. So yeah, so any doubt? If you have any doubt, you can ask. Also, do you guys know that this microstate table also gives me the number of actual terms associated with D2? I think I will be covering it in some other questions where some term symbol is asked. But it was interesting. So you have no doubt? Okay, I will like to take your suggestion because your feedback is important. So I have played a total of 3 videos, and if you have like any, if they are very like for this particular one, I have made the video of long 17 minutes because I thought that this concept was important to share. So if you think that this is unnecessary, you can just tell me every feedback. You can give me in the chat box. Yes, Sankari. Actually, so we are divided the questions at paper for we are a bunch of, I think, around 10 people or what, but you are getting the live interaction with every week, not every week, yeah, every week in like a set of slots. I think there are 7-8 slots. So we are actually asked that to do a minimum of 4 questions. So if I can do the 5 one also, but the problem is that we need to continue it for the 12 weeks, and I have already been allotted till 2017. I have chosen the set of question I will do. So it's actually tough to get number of questions also, because there are a lot of people making videos. We are divided ourselves that what we will be choosing. Also it's a 1 hour session. So anything else, Sankari? So you guys are also attending other live sessions, and if you have any other feedback regarding this live session, how this should be conducted in some better way, you can tell me, so that I can communicate your feedback to the authorities. So what you guys are doing actually right now? MSc, PhD, BSc? Yes, Ravindra. Yeah.
Now,
You can, I think, type on the chat box. Your voice is not clear. Yeah, that's a very nice question. Number of microstates same in 3D2, 4D2 system. Oh, so thinking of that, this 3 and 4 number, this is the quantum number, the principal quantum number, correct? So this is just increases as my element atomic number increases. It goes, the element is becoming larger, in a sense. So I think that the number of electron in that particular d orbital, it will be again it is the d orbital, so it will be having the same structure, T2g Eg, in the octahedral field, and again the 2 electron will occupy the space. Actually what we are doing, we are finding the probability where my electron will be. So I have explained in the video, like in the ground state, if I say, for example, if it is in this 2 orbital and then goes and do some transition. So that was just a concept, and you can understand how these 45 microstates are generating from there. So for the same 2 electron in d orbital, whether it is 3 and 4, I think the number of microstate will be same. I think not, but it is same. Yeah, nice question by the way. Okay, Sankari, nice. Okay, most of you are doing masters. Some of you have completed your master. Okay. Oh, you told, yeah, integrated MSc. Suraj, I think it is SAJ Dutt. You are doing your master from where?
Ma'am, are you asking me?
No, this okay. Dutt has said na that he is pursuing masters. So I just asked. I'm just asking these questions to know my actual audience who are attending till the last. Okay, nice. So if you have any questions from your side, because we have been asked that if you guys need some, you have other question related to careers and all, then we need to answer it also. Okay, most of you have it's a 50-50, yeah. Two of you have completed masters. Okay, so from where you have completed your master, Gunasli? Also, actually, I am very curious to know how you guys know about this gate portal. I mean, uh, because okay, nice.
Ma'am, our university informed about this portal through a communication platform on email. They sent email to us, so we connected to you, ma'am.
Nice. Because still, I think there should be some promotion for this gate portal. I mean, not only gate but NPTL itself.
Actually, me normally searching Google in CSA net and the GATE exams ma'am about that. So automatically this notification came to me.
Oh, very nice.
Yeah.
Okay, so all the best to all of you. Okay, so I'll take the leave. Thank you.
Thank you so much, ma'am.
Thank you, ma'am.
Yeah, okay.